Now that we've seen a variety of functional groups and a variety of families of organic compounds, we are going to turn our attention back to the simplest family of organic compounds, the alkanes. After a brief introduction, we'll talk about how to name alkanes. We'll take a quick look at alkane properties, and then we'll focus on a new topic, alkane conformations. Alkanes have the general formula CnH2n plus 2. So for any whole number n, we have 2 times that many hydrogens plus 2 extra hydrogens. So for example, if n equals 1, then we have 2 times 1 is 2, add 2 more, and that gives us 4 hydrogens. So this is CH4. If n equals 2, we have C2H. 2 times 2 is 4, add 2 more is 6. Now, working with this formula may seem rather pointless when we have very small molecules, because if we have 1 carbon, we can quickly fill in our 4 hydrogens to give carbon 4 bonds. If we have 2 carbons, then we fill in our hydrogens, and we can see that we have 6 hydrogens, so we know the formula is C2H6. But using this formula becomes a little more handy when we get to larger molecules. I don't really want to have to draw out everything just to figure out how many hydrogens I have. So now let's look at one more example using C10. That gives us H22. By knowing this formula, we can easily determine how many hydrogens there are supposed to be given a particular number of carbons. As we think about our simplest alkanes, we have CH4. Here we have just 1 carbon, and this is called methane. With 2 carbons, we have C2H6. So 2 carbons is called ethane. And then C3H8, where we have 3 carbons, this is called propane. So in general, as we are naming alkanes, we have the ane ending, or the suffix, which tells us that we're just talking about alkanes so that we have all carbon-carbon single bonds. And then the prefix, the meth, eth, or prop, that gives us information on the number of carbons. So here we have the 3 simplest alkanes. Let's keep looking at larger molecules. As we get larger than 1, 2, 3 carbons, we can continue with the N-alkanes. So N stands for normal, which means straight chain. Now, this is not straight chain in terms of 3-dimensional shape. It just means that there are no branches. So that in all of these molecules, we have CH3s on the ends, and then everything in between is CH2s. And this is referred to as a homologous series where they differ by only a CH2 unit, which is called a methylene unit. We already talked about the simplest alkanes having the suffix ane and the prefix giving information on the number of carbons. Well, in terms of common names for these compounds, we're going to continue with that. So here we have 4 carbons, and the common name would be N-butane. This has 5 carbons. This is N-pentane. 6 carbons, N-hexane. 7 carbons, N-heptane. 8 carbons, N-octane. 9 carbons, N-nonane. And 10 carbons would be N-decane. So keep in mind for each of these, the ane ending tells us that we have all carbon-carbon single bonds. The parent name tells us how many carbons we have. So bute is 4, pent 5, hex 6, hept 7, oct 8, none 9, and dec 10. And then in this case, the N tells us about the connectivity. This tells us that they are all straight chain. They are not branched. Okay, so a couple slides ago, we talked about methane, ethane, propane. Now with C4H10, that is butane. But unlike what we saw with our first three alkanes, we have two different possibilities for how these four carbons can be connected together. We could have them in a straight line, as we just saw, or we could have three carbons in a line and then a branch off of the second carbon. So we have different connectivity, and so these are constitutional isomers. They have the same molecular formula, C4H10, but they have different connectivity. So they are constitutional isomers. So these compounds are going to have very different properties, different chemical properties, different reactivity, in other words, and also different physical properties. For example, the top one has a boiling point of negative 0.4 degrees Celsius, and the bottom one, its boiling point is negative 10.2 degrees Celsius. So definitely different compounds with different properties. So the name butane isn't sufficient to be able to distinguish the compounds. So with methane and ethane and propane, there was only one way that those atoms could be connected together, and so the name methane or ethane or propane corresponds to only one compound. But when we're talking about C4H10, now we have two different possibilities, and so we need to be able to distinguish them by name. So the top one, as we just mentioned on the previous slide, this would be called N-butane, and then the second one is called isobutane, where iso refers to having a methyl branch off of the second carbon. Next, if we look at C5H12, this would be pentane, but we can draw this as 5 carbons in a chain. We could have 4 carbons in a chain and a methyl branch, or we could have 3 carbons in a chain and 2 methyl branches. So the first one would be named N-pentane, specifying that it is normal, that it is straight chain. The second one is isopentane, and the third one is called neopentane. So what we're looking at here are some of the common names for alkanes. Throughout this year, we're going to find many examples where it can be very useful to classify our carbons. And so what we're looking at is what type of a carbon is it? In other words, how many carbons is it connected to? So if we have a carbon that is connected to only one other carbon, that would be a primary carbon. If we have a carbon connected to 2 carbons, that's going to be secondary. If a carbon's connected to 3 other carbons, that is tertiary. And if we have a carbon that's connected to 4 carbons, it is a quaternary carbon. So let's come look back up here. This carbon here is connected to only one other carbon. So this one is a primary carbon, and so is this one, and this one, this one, this one. This carbon is connected to 2 carbons. This carbon is connected to 2 carbons. And so these are secondary and secondary carbons. And then here, this carbon is connected to 3 other carbons. So this one is a tertiary carbon. If we look at the pentane isomers, this is primary, 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 and primary. This is another primary. Each of these carbons is connected to only one other carbon. This one is secondary. It's connected to two others, secondary, secondary. This one here is secondary, but this one is connected to three groups, so that is tertiary. Specifically, it's connected to three other carbons. And then finally, this carbon is connected to four other carbons, so this is a quaternary carbon. Being able to classify carbons becomes important as we start to think about reactivity. We're going to find that functional groups connected to primary versus secondary versus tertiary carbons are going to react differently. They will react at a different rate, and in some cases they react by a different mechanism. In addition to classifying the carbons as primary, secondary, tertiary, quaternary, we can also classify the hydrogens, although we're not going to use this quite as often. So here we have three hydrogens, and because those hydrogens are connected to a carbon that's connected to one other carbon, then those are called primary hydrogens. Here we have two hydrogens that aren't drawn, but we know that they're there. Those two hydrogens are on a secondary carbon, so they're called secondary hydrogens. Here we would have one hydrogen connected, so that would be a tertiary hydrogen. Here we have no hydrogens connected, so we can't have a quaternary hydrogen. Another thing that's important to discuss would be alkyl groups. So an alkyl group is typically how we would refer to a branch, for example. So notice that looking at this compound here, we have this 3-carbon chain, and then here we have a branch. And so this branch is a CH3 group. So keep in mind that this is methane. So this, where we have a CH3 and it is connected to something else, this would be called a methyl group. So we drop the ANE and we replace it with a YL ending. Actually, that's what we already did here, because from an alkane, we get an alkyl group. This is going to be necessary as we are naming branches, and later we're going to see how this is also used in naming different families of organic compounds, such as alcohols and alkyl halides. And then one other thing to mention before we move on is the idea of R groups. If I was talking about a primary carbon, I could say that I have an R group connected to a carbon that's connected to 3 hydrogens, where R is just a generic part of the molecule. I like in the book they mention you can think of the R group as the rest of the molecule. And in some cases, we don't care about what else is in here if we are focusing on this particular carbon that is a primary carbon. So you need to become familiar with the idea of using R as really as an abbreviation or a shorthand for the whole rest of the molecule. Let's continue to look at larger alkanes. So with C6, we are talking about hexane. Here we have a whole group of hexane isomers. So we can have 1, 2, 3, 4, 5, 6 carbons connected in a row. Or we could have 1, 2, 3, 4, 5 with a branch off the second carbon, or 1, 2, 3, 4, 5 with a branch off the third carbon. If I had 1, 2, 3, 4, 5 with a branch off the fourth carbon, that's just the same as this. But we're still not done. We can have 1, 2, 3, 4 carbons with 2 methyl branches off the second carbon, or 1, 2, 3, 4 with a methyl group and another methyl group. So with hexane, we have 5 isomers. And let's see, we already know that this would be called N-hexane. This one would be isohexane because we have a methyl branch off the second carbon. Ooh, I'm not sure. I'm not sure. Hang on, we'll come back to that. C7H16, now we're looking at heptane. Okay, we can have 1, 2, 3, 4, 5, 6, 7. We can have 1, 2, 3, 4, 5, 6 with a methyl branch. 1, 2, 3, 4, 5, 6 with a methyl branch. Those are our two options. We can have 1, 2, 3, 4, 5 with two methyl branches. 1, 2, 3, 4, 5 with two methyl branches. 1, 2, 3, 4, 5 with two methyl branches, or 1, 2, 3, 4, 5 with two methyl branches, or 1, 2, 3, 4, 5 with an ethyl branch. And then finally, we can have 1, 2, 3, 4 carbons with a methyl branch, another methyl branch, and another methyl branch. And now we have 9 isomers. Let's see, we know this one would be N-heptane. This one would be isoheptane. But then we have a whole lot of question marks. If we look at C8H18, this would have the parent name of octane. Here we have 18 isomers. With C9, nonane, we have 35 isomers. And with decane, we have 75 isomers. So when we're talking about relatively small compounds, it's okay to use the common names. We can distinguish the butane isomers as N-butane or isobutane. Having to memorize 3 common names, N-pentane, isopentane, neopentane, that's manageable. It's not fun, but it's manageable. But as we're getting to larger and larger compounds, it is ridiculous to have just a bunch of common names. So sticking with common names is not reasonable, and instead we need a systematic approach to naming organic compounds. And that's what we're going to look at in our next video.